Okay, here is another simple Mendelian genetic problems, but we're going to use probability for this. So some new learning is coming up here. So PKU, ketonuria, is a rare genetic disorder that causes an amino acid phenylalanine to build up in the body. This disorder is caused by a defective gene that normally breaks down phenylalanine, which can cause severe brain damage. It's a recessive trait. So suppose two people who are carriers for PKU are planning to have 3 children. You are their genetic counselor. What is the probability of each of the following? Number one, they want to know what's the chances of all 3 of their children to be normal? What are the chances of 1 or more of their children to have the disease? What about the chances of all 3 children to have disease and at least 1 child will be phenotypically normal? So let's just start with the idea of carrier, because that's another way of saying recessive, right? So I'm just going to use, again, you can use whatever letters you want. So I'm just going to use A will be normal phenotype, so no disease, no PKU. And then A will be the recessive PKU. And it says that 2 people who are carriers, so we know that they carry the trait. And they want to have 3 kids. So they want to know what are the chances. So again, just do that real simple Punnett Square, and we're going to refer to that throughout this problem. So I'm going to make this kind of small off to the side, but it's going to be helpful. So again, you could share with them, your genetic counselor, how a Punnett Square works. So I'm going to do this. All right, so parent 1 has 50-50 shot, right? Can either have a gamete that's carrying the normal allele, or it could have the gametes carrying the recessive. So 50-50 shot, egg or sperm will have either normal or recessive. And the other parent happens to be the same way. So here's all your possible combinations upon fertilization, right? To start simply, you would have a 1 in 4 shot every time you have the child, a 1/4 chance that it could have PKU. And then there's a 3/4 shot that it will be normal. And that's the genetics gamble, right? So that is their basic offspring. But they want to know, they said, look, we're planning on having 3 children. What are the chances of all 3 children will be normal, 1 or more, blah, 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 blah. Okay, so this is where we need to use some probability. And so there's really 2 rules of probability that are applied to, well, these are 2 basic rules for probability applied to genetics. So I'm just going to insert table here. So there is what we call the rule of multiplication. And there is the rule of addition. And here is basically how they work. So for the rule of multiplication, this rule, it states basically that the probability that is spelled right. Okay, so the probability of events occurring simultaneously is the product. So multiply is the product of their individual probabilities. Okay, so I'll just explain this in a second. First time I heard this, I was like, what are you talking about? Okay, so here's the simplest way to think about this is coins, right? So you have heads or tails, right? So you have 2 coins. What are the chances of both coins being flipped and ending up heads, right? Of both ending up heads, right? So this would be a simultaneous event, right? So heads on one and heads on the other, and what are the chances of that occurring? You could do it like the chances of tails. It doesn't matter. So let's think about it. Coin one, you got a 50-50 shot. So 1 and 2 shot of ending up heads, right? And this is going to be a keyword, and coin two, same thing. You got a 1, you got 50-50 shot. Okay, I don't know why I ended up that way. There you go. So, and implies multiply of these happening together, this and this. So very simply, we take 1/2 times 1/2 equals 1/4. So you got a 1/4 chance that you would get, if you have 2 coins, that it would, you'd flip them both, they end up being heads. So whenever you want to use the rule of multiplication, I need you to think and, right? This and this happening. What are the chances of this and this happening? So that is the rule of multiplication. Now we'll do addition and then we'll apply it to genetics. So the probability, I'm just, I'm doing a copy and paste. Now I'll just do it. So the rule of addition says the probability of events occurring in 2 or more ways is the sum of individual probabilities. Okay, and again, I'll give you the coin analogy and then we'll look at the Punnett Square, although you might already be seeing it. So you have 2 coins again. What are chances of ending up with heads and tails? Okay. Well, again, there's 2 ways that this could occur, right? You could have the first coin end up heads and the second coin end up tails, or you could have the first coin end up tails and the second one end up heads. So you need to take into consideration probability of those events occurring, right? So 2 ways this could happen. You could have tails, heads, or, and I mean, this is a big word, or you could have heads, tails. So let's do the probability. So again, to get tails on a coin, that's a 1 in 2 chance of tails ending up when you flip the coin. And then again, if a tails and a heads show up, it's a 1/2 chance for the other coin to be heads. Okay? So that's 1/4 chance for that first possibility of occurring. But keep in mind, we could also have this. So this could occur, or this possibility. So or is a really important word. Or we could have a 1/2 chance that the heads pops up first times, then the 1/2 chance that tails shows up secondly. So that's the other possible way that we could get that combination, right? So we have to add we have to add the 2 different possible ways we could get heads and tails. So we have a 1/4 chance that it would turn out this way, 1/4 chance that it could end up tails head first, or, so that's plus, a 1/4 chance that it could end up being heads, tails. Either way, it's heads and tails. So that you have a 50% chance, right? Okay, so think 4. I also, in terms of genetics, I want you to think of like this, right? You have a 1/4 chance of getting heterozygous and a 1/4 chance of getting heterozygous this way. So this is your 50% chance of getting heterozygous. And then this is 1/4 chance getting homozygous and a 1/4 chance. So if this is like, what? Just look at your Punnett Square. This is a 1 in 4 chance of getting this, a 1 in 4 chance of getting this. Sorry, I should say it this way. A 1 in 4 chance getting homozygous dominant, 1 in 4 chance getting recessive, homozygous recessive, and then a 1/2 chance of getting heterozygous. Okay. So let's put this to this. I think it'll make more sense once we actually start looking at the problem. To address the first one, their first question, what are the chances that all 3 of their children will be of normal phenotype? Okay, so this is like all, like this, my first and my second child and my third child are all normal. So, and this is the rule of multiplication. So what are the chances that your child is normal? Well, if we go to our Punnett Square, you have a 3/4 chance for a normal phenotype, right? So 3/4 chance, again, this is times, because I want to know that my first and my second and my third child are normal. So all 3/4 shot being normal, multiply them together. 3 times 3 times 3, 27. 4 times 4 times 4, 64. Okay, so you have a 27 out of 64 chance that all 3 of your children will end up normal. Okay, so now this one's a little trickier. But if you think about this one, they want to know what are the chances that 1 or more of the children will have the disease. So another way to say that is like this. Either all 3, all normal, or not, right? They're either all normal or 1 or more of them have it. So this is the rule of addition. So all normal, we just figured out, was 27 out of 64, plus the chance that that doesn't happen, and it's an either or, right? So that's 100% chance that they're either all going to be normal or they're not. So that's 1, right? So then you simply do the algebra and you take 1 minus 27 over 64, and you figure out what the chances of or not. And that will be 37 out of 64. Okay, because keep in mind, then you have to convert 1 into 64 out of 64. You know, all that pre-algebra that you learned, it's going to come back and get you. Okay, what are the chances that all 3 children have the disease? Okay, so again, this is my first child and my second child and my third child have the disease. So the chances of getting the disease, if you go back to your little Punnett Square, is a 1 in 4 chance. So I have 1 in 4th chance that each of the children, again, this is a simultaneous event. I know they might not give birth all at one time, but they might. You never know. They're triplets. Anyway, so 1/4 times 1/4 times 1/4 gives you 4 times 64. Yeah, same thing. So 1 times 1 times 1 is 1. 4 times 4 times 4 is 64. Okay, so pretty slim chance that all 4 will have the disease. And then D is very similar to B. What is the chance that at least 1 child will be phenotypically normal? Again, you can state it like this. All with disease or not, right? Or at least 1 is okay. Algebraically, same thing. 1/64 is the chance that all have the disease. Plus, we don't know, but they all have it or they don't, right? Or at least one of them doesn't. So 1 minus 1/64, you do 64 out of 64. And then you get 3 out of 64 chance that at least 1 of your 3 children will be normal. And that's how you apply the rule of multiplication and the rule of addition. There's other ways to apply those too, mainly like if you have ginormous tri-hybrid Punnett squares or even bigger. T